I'm ready.
Go.
Okay. Thank you. That's me in Klingon. So I don't know. Hopefully it's not too serious. This is not really what I'm going to talk about because I think Yakir will talk a little bit about that, and maybe Sandhu tomorrow. But this kind of motivates what this talk is about. 10 years after the AB paper, Yakir and Pendleton and Peterson came up with their preferred interpretation of the AB effect. And because the justification for it was that they only wanted to consider, gauge invariant quantities that are measurable. And they wanted to have a one-to-one relationship between what every part of the theory and what could be measured in principle. So they said that they argued that they wanted to consider the E and the B fields as real, but yes.
Stay here.
Oh.
Because they have to look at.
Oh, okay. Sorry. All right. I'll try to point like this a little bit. So they argued that really the A and the B fields are real, but they have a non-local interaction with the particle that goes around it. All right. So that kind of just sets the stage for it. And a lot of what we talk about is actually reviewing somewhat this famous paper from 40 years ago, Aharonov, Pendleton, and Peterson. So also to set the stage is trying to kind of, change the perspective on the famous two-slit experiment. Usually we're taught, and certainly every textbook I've ever seen, we've been taught to think about the two-slit experiment in the same way we think about classical interference. That there's really, like a Schrodinger wave that's like a classical wave. But really, if we go back to the dictum from the slide before, that we want to have a one-to-one relationship between every element of the theory and what you can measure in principle, you actually can't see the Schrodinger wave in general, except for ensembles. And also, just as a kind of a intuitive perspective, oftentimes you can confuse the kind of classical intuition that we have with waves with the Schrodinger picture. So this talk is motivated by trying to understand how do you think about interference from the perspective of a single particle, particularly if you have a particle going through the right slit, how does it know whether or not the left slit is open or closed? And then, famously, Feynman said that nobody knows how it can be like that. So a couple slides of review. The point here is that almost everything that's been done up to this point to study the two-slit was done from the perspective of studying observables which were moments of position and momentum. So to give of course, you all know that interference is parameterized by the relative phase between the left and the right wave packets for a single particle. Let's see, it's working. Yes. But if you actually look at all the moments, averages of the moments of the position momentum in that state, psi alpha, you see that none of them are dependent on this relative phase. And there's a beautiful proof of this by that paper from 40 years ago. And it's easy to see how this is true, that if you look at, you plug in this wave function into this expectation value, you see that the only thing that could possibly depend on the relative phase, alpha, are these cross terms. But in order for it to survive this integral, actually the x to the n or p to the m have to make the left or the right wave packet overlap. And of course, they can't do that. So in fact, the averages of any power of x or of p is not dependent on this relative phase. So this suggests that maybe these are not really the best observables to look at. In fact, they're in my opinion, and Yakir's opinion, not the right observables. So what are the right observables that are sensitive to the relative phase? Well, these are operators that are actually exponentials of, for example, position and momentum. And these operators actually translate the different lumps of the wave function, for example, in a double slit, so that they overlap. So e to the I over hp times a distance is actually just a translation operator. So that makes this right-hand lump translates it and makes it overlap with the left-hand lump. And if you actually calculate the expectation value for those operators, you see that they are dependent on the relative phase. what exactly does this tell us? What exactly does this expectation value tell us? Well, it tells us something about what's called modular variables, which Yakir introduced. So, yeah, everybody knows what a modular variable is. If you any periodic function is really a function of these modular variables. So, and they go, they behave just like any kind of angle, really. So you can do a one-to-one mapping between an angle and every value of the modular variables. And this is actually the range of it for the momentum, modular momentum. Okay, and then the other crucial distinction, just to review, is that these modular variables actually satisfy non-local equations of motion. That's really a whole new show. That's a whole different sense of non-locality, in contrast to what we usually think about in terms of EPR type of non-locality. But so if you look at the Heisenberg equation of motion for these kinds of observables, ddt of EDI or H PD, you see that it actually looks at the value of the potential at one place and subtracts the value of the potential at another place, where D can be very large, can be very far away. And so this means that, suppose here's a double slit setup. We have a particle that's localized around the right slit. You actually have modular variables that are changing depending on the difference of the potential between these two different points. Now, this is something that has no counterpart in classical mechanics. So in classical mechanics, if you're trying to look at time rate of change of some, for example, a function of p, then you look at the Poisson bracket, and you can see that there's no non-trivial solution to this kind of expression. In other words, the only way you're going to get a time rate of change to the function of the momentum is if you have a local gradient basically in your potential at that point. But in this case, what happens, since we're now looking at we're going to be looking at situations where we have one particle localized around one slit, you're actually going to see that those modular variables are actually sensitive to the difference in the potential. And I'm not going to go into much detail about how this is actually done, but just to give you an example, if you had a situation where both slits were open, then you can see that actually this modular variable is conserved, right? Because the difference in the potential between the points is 0. Whereas if you close a slit, then actually it's not conserved. The modular variable will change. So, all right, we're almost to the end of this beautiful paper by Yakir and co-authors. So suppose we set up a situation. Here's your double slit. We set up a situation where the particle is localized around the right slit, and now we've argued that there are these modular variables which are sensitive to whether this left slit is open or closed. So there's like an action at a distance between this slit and the particle that's localized around there. Can you actually observe it? This would be extraordinary. I mean, it would be, this is real action at a distance. You would think that would actually violate causality. And actually, beautiful proof. I think it's one of the most beautiful proofs I've seen in quantum mechanics. Yakir proved that exactly in this situation where it looks like it's about to violate causality, the thing that's actually exchanged non-locally becomes maximally uncertain. Gets completely, even though it's exchanged non-locally, even though it's a non-local equation of motion, you can't observe it. And so he proved this very generally. So whenever you get into a situation for any modular variable, when it looks like you're about to violate causality, you can't, because it becomes what you find in this new concept of completely uncertain, meaning the probability distribution for those modular variables, like in this case, like an angle, just goes completely flat. So this is kind of very disappointing. I mean, how is it that, we go back to the original dictum, we want to have a one-to-one relationship between what can be, each element of the theory and what can be measured in principle. It's kind of a downer, right? If you can't measure the thing that's exchanged non-locally, then why am I up here arguing there's non-local equation of motion? So now we finally get to the point of what's new. And what's new, and just to coin any of you who've studied with Yakir Here's a favorite expression. He says, having your cake and eating it also at the same time. And I'm amazed. He's done this so much. He's had his cake and eaten it so many times. I can't believe you haven't put on more weight. But this is a typical example of having your cake and eat it. So here's the problem. We know that if we start with, this situation, the state of the wave function for the single particle, which it's, psi right plus psi left, then in that situation, we know that the thing that eventually is going to get exchanged non-locally, the modular momentum in this case, we know that it's definite. But if we start off with the situation of psi right plus psi left, then we can't even start to argue that the particle is definitely one slit, and we want to see what the effect is of open or closing left slit on this particle that's over there, because we're starting off in a state which is psi right plus psi left. So that doesn't work. The other problem is that how are we going to get around the fact that if we do set up the problem from the get-go, such that the particle is definitely at one slit, we're going to open and close the other slit and try to see this non-local exchange. How do we get around the fact that you can't prove that exactly in that situation the thing that's exchanged non-locally becomes completely uncertain? So that's the second problem. And then obviously the third problem is even if we could get around the second one, we can't violate causality. So how do we do all these things, these three things together? And so that's the answer to having your cake and eating it. And the way this is going to happen is by using pre and post selection to arrange for both a localized particle at one slit, but also on your post selection to have a situation where you can actually see this non-local exchange of modular momentum. And what we're going to end up doing is actually doing a weak measurement on this modular momentum. And you can prove that by doing that weak measurement, you don't actually disturb it. You don't kick, or you kick very few particles from the right slit to the left slit. Okay. And then finally, we'll do a post selection on an ideal measurement of that same modular momentum. So just very quickly, the way this is done, we do a pre-selection on the particle at the right slit. We're going to do a weak measurement. And you've all actually given a very nice review of what weak measurements is, but it's given by this expression. And we're going to weakly measure a modular variable. In the particular case, we're just looking at side, left plus right or left minus right. We can actually do the parity. Next thing that's going to happen in time is we open and close the left slit. And then finally, we're going to post-select on an eigenstate of parity, namely as if it was in both slits. So this is my last slide. Here's actually, it looks kind of complicated. This is a depiction of a experimental proposal. Here comes in, this is two Mach-Zehnders. Here's a double slit. This is like doing the pre-selection. You arrange the amplitudes in such a way that the particle definitely goes to the right slit. Here's where you do weak measurements of the parity, and here's where you do the post-selection. And to get to the upshot here, what you've got is if you leave this left slit open, and either leave it open or you're not doing a measurement there, then what you see is that each particle, of course, in a weak measurement, you have to use a lot of particles to get the signal because each one doesn't give you a lot of information. But the point is that each particle delivers a shift to the measuring device corresponding to the weak value of the parity equals 1. And here's just a specific example of what the weak values are in different arms of this setup. In the second case, you close the left slit, or you do a measurement over here, strong measurement. And even though you can show that almost no particles, these weak measurements just kick very few particles from the right slit to the left slit. Even though almost no particles go there, this opening or closing the slit or doing a measurement over there has a dramatic impact on the weak measurements that happened in the past. It has a huge difference in what those values are. So my final summary is, question is, can you explain the results of that experiment in terms of local interactions? And again, the weak measurement that we did before the whole setup went into the two slits, you can prove that even though you did that weak measurement, only a few particles, independent of the total n number of particles that actually go through, that you actually do the experiment with, only a few of them go through the left slit. nonetheless, you have this huge difference in the measurement of this non-local observable. So the question is, you can't, because you only have a few particles that you can use to explain the fact that all n particles deliver this shift in your measuring device. Those few particles can't actually do it. Okay, and to summarize, this is the beginning of a story for a whole new way of thinking about quantum mechanics that you can introduce in terms of the Heisenberg picture. And it's based on the ability to have an ontology or description of quantum mechanics in terms of single particles. And so in the case of the double slit or multiple slit, this allows you to have an ontology that instead of a quantum wave that goes through all the slits, you have a single localized particle, and it has non-local interactions with the other slits. And I recommend very highly Akir and Danny Rohrlich's book.
Okay. Thank you very much.
Thank you.
Now we have a few minutes, maybe 2 minutes for questions. One question. There's a question here. Okay.
Here first.
Oh, yeah. Huh?
Did you have a question?
Do you know what I'm talking about?
Can you go back to the Maxim?
I wanted
Sure.
just to ask who is Schrödinger and who is Heisenberg.
Explain what is the picture there.
Well, down here?
Yes.
Oh, this is the, I don't know who found it. Maybe Danny found it. This is
I
a,
didn't know about it already.
oh, you can't know about it. It's a picture of the New Yorker. Huh? Oh, so if you can't quite see it here, but you got skiers, and one of the skiers, one leg goes around the tree on one side, the other leg goes around the tree on the other side. So you have,
Yeah, but this is
Mac-
a book Daniel Diakin wrote.
Yeah. Yeah, this is a fantastic book. It's going to become a classic.
You can sign which is.
You mean down here?
No, up on the 2 pictures are signed.
Oh, yeah, Schrödinger and Werner Heisenberg. You can't see, right? Heisenberg is, the operator perspective. There's no real reality. Okay, it depends on.
Can you go back to the Maxim?
Sure. Okay.
Just, I didn't understand why you need you seem to have really 2 Maximers here.
Yeah.
Why do you need the bottom one? All the action seems to be happening up.
Well, this just prepares the pre-selection.
Okay, you're preparing a.
That's the blue line. And then you also want to do the weak measurement before the particles actually get into the. So this is having your cake and eating it. You want to have both the particle-like property localized at a slit, but also, the clincher is before, when you localize a particle, the modular momentum that's exchanged became completely uncertain. But now, if you do the post-selection on a definite state of modular momentum, then you can have both together. That's what's new.
Those 2 weak measurements are actually 1 weak measurement of the parity of down below.
Right. Right.
Just didn't understand. So does this violate causality or?
No. Okay. Sorry. Thank you for asking. That's the other clinch. So when you got to this point, okay, where is it? When I said, how do we do it in a way that we don't violate causality? I think you can prove that the only way you can do this without violating causality, is use pre and post selection. Because just like in the AB effect, where you have to bring things together to see the interference phenomena, and you have to wait till you do the post selection to see what was the result of the weak measurement that you did in the past. So for that same, because it's simply the sandwiching and topology of the situation, you can't violate causality. Thank you, though. Okay.